Good morning, good day, or good afternoon, wherever you join us today. Welcome to our webcast from Model to Mission, Software Development and Integration in Safety Critical Aerospace Systems. This webcast is provided to you by MathWorks DLR and SYSGO. DLR, MathWorks and SYSGO have teamed up to present how model-based design accelerates development and supports certification processes for safety-critical avionics systems. My name is Franz Walkenbach and I'm the Partner Manager at SYSGO, and I'm glad to be a moderator today. And with that, I would like to introduce the speakers for today. Let me please start with Juan Valverde. Juan is the Aerospace and Defense Industry Manager for the EMEA region at MathWorks. His technical background is on the design of dependable embedded computing solutions for aerospace. Prior to MathWorks, Juan was a principal investigator for embedded computing at the Advanced Technology Center for Collins Aerospace, Raytheon Group in Ireland. Juan has a PhD in microelectronics and computing architectures by the Technical University of Madrid in Spain.
Next, I will follow up with Bojan Lukic. Bojan is a research associate at the German Aerospace Center DLR within the working group of avionics systems. The main responsibility of Bojan is the model-based development of safety-critical systems in aviation. Currently, Bojan works on the development of the next generation avionics architectures. For this, he explores formal methods for the automated configuration of integrated avionics systems. Envisioned is a third generation of avionics with stateless functions and the capability of dynamic reconfiguration. Next, I will continue with Matthias Klimek. Matthias joined SYSGO in 2023 and works as a software engineer and software architect. He is involved in different projects for driver development and system integration. Before joining SYSGO, Matthias developed software for bare metal embedded devices with strong connection to the underlying hardware. Matthias studied information systems technology at the Technical University of Darmstadt in Germany, during which he spent 1 year at the INSA in Rennes in France in the Erasmus Student Exchange Program. And now let me go through the agenda for today. So we will start with company introductions by each member. And then we will present our motivation for IMA, so Integrated Modular Avionics, modeling and reconfiguration. Then we will follow up with PikeOS. What is PikeOS as an RTOS and hypervisor, and what role does it play in the whole activity? And then Bojan will go through the integration, meaning the software architecture, code generation and deployment. And we will also show a nice video of the demonstrator that we have created. And then to finish up, we will present the custom added value as a key takeaway. And with that, I will hand over to Juan. Juan, please take it away.
Hello, everyone. And thanks a lot, Franz, for the introduction. Yeah, I would like to say first a few words about MathWorks, what we are and what we do. So MathWorks is the developer of MATLAB, Simulink, System Composer, and more than 100 vertical products that support analysis and simulation for scientists and engineers, of course. While MATLAB is the overall programming environment and language, Simulink offers a graphical representation for the design and verification of models. Then System Composer, that can be seen as a layer on top of Simulink, will help you capturing architectures both for system level and software or hardware. Then at the end, what MathWorks does is creates a unified environment where we can see System Composer as the main integrator and orchestrator, and it will connect the requirements management solutions, ours or third party. It will allow you to run analysis based on MATLAB, use all the power of Simulink and all the state flow. You have here like Simulink fault analyzer, Simulink test, all the verification tools, and bring designs also from third-party, legacy code, etc. So the idea is that you have an environment that will help you with this. As MathWorks, we collaborate a lot with many companies and centers. And of course, one of them is the German Aerospace Center, DLR. So Bojan Lukic is going to give you a few words about it. Hello, Bojan.
Hello, Juan. Thank you for the introduction. Coming to the introduction of the German Aerospace Center. So the German Aerospace Center, or also called in short DLR, is Germany's national space agency. I sometimes like to call it Germany's NASA for people who are not completely familiar with the institution. And we're doing various research, mostly in transportation, so space, aviation, but also automotive, but then also in energy, security, digitalization. At DLR, we're doing planning and implementing of the country's space program, and we develop sustainable solutions for societal challenges. So at DLR, as a research institution, we're trying to publish as much of our work as possible and show our results in papers. So if you're interested in publication papers, our work in general, I recommend looking at our papers where we show more technical details of our work. Handing over to Matthias from SYSGO.
Thank you, Bojan. Hello also from my side. I will introduce SYSGO and our product. SYSGO is the European leader for embedded operating systems, including our flagship product PikeOS, which is a certifiable real-time operating system, including hypervisor for safety and security applications. Ilinos, which is our own embedded Linux distribution, capable of running standalone, but also on top of PikeOS as a guest OS. And PikeOS for MPU, which is an RTOS made for MPU-based architectures without requiring an MMU. We are worldwide a key player in most markets where safety and security of the system is important. This includes aerospace and defense, space, railway, automotive, and the industrial and medical sector. So we have over 30 years of experience, and alongside our software products, we offer services to support product development, BSP development services, and long-term support and maintenance. We are also a member of the Thales Group. With that, over to Juan, who will introduce the application of today's topic.
Thanks a lot, Matthias. So yes, before we start with the integration details, I would like to provide a bit of context to see where we are today. So today we are talking about using model-based design and model-based systems engineering for aerospace systems. If we were to simplify the development processes and show it in this fashion, right, in this integration versus fidelity, we could differentiate between three major layers. This is mission engineering, platform design, and integration, and then, of course, the hardware and software design layer. What is very important to highlight is that moving around this canvas is done, and until we get, of course, to the highest levels of fidelity that you can see on the right side, we do this using models. And models can have different levels of fidelity, of course. We can actually see the V model on top of these, right? Where we see that the requirements are flowing down, then validation is done and go up again. And then design goes again down through the different layers. And then, of course, integration goes up again. So we do not need to have all levels of readiness to move around the canvas. What is very powerful is that we can actually start integrating early, we can start validating early, and this is one of the main advantages of model-based design, shifting left and moving and doing things earlier. Today, we are not going to talk about the whole design lifecycle, of course, but we are going to touch systems and software design all the way until the integration with a real-time operating system, PikeOS, that is designed by SYSGO. Since we are today talking about systems integration and software architectures, we need to mention, like Franz introduced already, what IMA, or Integrated Modular Avionics, is. IMA is an aircraft electronics architecture that consolidates many previously separated avionics functions onto shared computing resources. This is instead of having one dedicated computer per function, this is the old federated models, IMA hosts multiple avionics applications on common processing modules. This is an approach that has been used for the A380, A350, F-35, and so on. This in general requires a following standards like ARINC 664, ARINC 653 for partitioning. We will see a lot more later. And then the application that we will show today, and Bojan will explain a bit later, is how being able to reconfigure dynamically at this level can be a great asset to increase performance, but also safety. But before Bojan explains this into more detail, I would like to show a bit of how we start capturing these designs. For that, let me introduce what the System Composer is. I already mentioned a bit as an orchestrator, as this integration platform. So the idea is using System Composer. Remember, this is a top layer or a layer on top of Simulink. In this case, this is just showing a small example of an architecture of a drone. In System Composer, one can capture a certain behavior, using, for instance, activity diagrams. We can also capture these using sequence diagrams. Then, since it is expected that we will have complex models with different layers, with many blocks, it is also possible to have different views. We can extract different views from these. What does this mean? I can extract only certain parts of my model. I can start only the functional level. I can extract the physical level, etc. Then you can create, for example, a functional architecture and physical, like I said, and then using the allocation editor, you can assign those different layers, and then you can play with different scenarios. And this is very important because one of the things that you can do is capturing metadata from your models. This will be very important to capture what we will see later, right? The software architecture, that is something that we can convert into something that PikeOS can deal with. And this metadata is captured via stereotypes. What is also very, very powerful is that MATLAB has an API that can read and write from these stereotypes. So you have all the never-ending analysis possibilities that MATLAB is providing. So you see a couple of features from what System Composer can do and when to use it. Then, since we're talking about fidelity and integration, imagine that you have a model in System Composer. This is exactly the same model as before, but you have different levels of readiness from the different components. So you could connect your model directly to the flight control computer, provided that you have an implementation already. This is, for example, using hardware-in-the-loop fashion. But then you might have other parts that are represented only by simple state machines or truth tables, or you might have already some detailed behavioral models in Simulink of your algorithms. Of course, within Simulink, you can have different levels of fidelity as well. Or you could even have code. You might have some legacy code. You might have other models that are coming from other tools and that you're bringing using FMI or FMU. So the idea, once again, is that you can architect your system or your system of systems in System Composer, and then you can run simulations from there, mixing these levels of fidelity. This is very powerful. At the same time, we can go one step farther. I already mentioned the hardware in the loop. Well, via hardware in the loop, we can bring the human in the loop, for example. If we have a real-time machine, in this case, this is the drone actually connected with SpeedCode, and then we have a human in the loop that is controlling the drone. We also have, of course, the connection with the visualization and 3D environments. So once again, the idea is having the different levels of fidelity can be mixed, and that we can go and iterate and add different variants. We can add different levels of readiness, and then we can continue working with this. But then what we're going to see today is what it means to have all these, capturing an architecture that can be an IMA architecture, and how it could be reconfigured. So, Bojan, I think if you can explain a bit more what this means, this would be very illustrative.
Yes, thank you, Juan. So we heard now from Juan the main theme of this presentation and the platform that we're working with, which is Integrated Modular Avionics. But to demonstrate some further how we can develop such a system with the previously introduced tools, we would like to introduce a use case, which is dynamic reconfiguration. What is dynamic reconfiguration? So simply said, in the context of safety critical systems, dynamic reconfiguration is the reconfiguration of functions or applications within the system. And it is used for improved resilience and dependability of the system. And it enables the system to adapt to unforeseen conditions such as faults and maintain safe operation. So what we can see here in the figure, for example, is we have 4 different partitions running within one processing module. periodically, so they repeat. And one partition, in this case partition 3, is switched with partition 4 through a reconfiguration. So we can assume that something is maybe wrong with partition 3, and we switch its functionality, or we take partition 4 to take over the functionality of partition 3. And this can be important to achieve, for instance, autonomy in such systems. So if we think about machine learning algorithms, which are talked about a lot recently, and the idea of using machine learning algorithms and more autonomy in avionics systems in the future, we might want to add some kind of safety net or safety layer, which could be dynamic reconfiguration. So in case this autonomous component in our system goes rogue or has some faults, we can fall back to a component which is maybe safer, and this component can then take over functionality again in our system. And dynamic reconfiguration within IMA can be done on different levels. So we're concerned with 2 levels mostly. The first one is the integrated level, as shown here in this figure. So we might have an aircraft system where we have different processing modules, here depicted as CPMs, which are connected through switches and some core network or network backbone for communication. We might also have sensors, actuators, or even legacy systems in this system. If we want to do dynamic reconfiguration on this level, we have to think about things like added latency through routing of information and the communication through the network backbone. So if we dynamically reconfigure the system during runtime between different processing modules, we have to keep these parameters in mind. And a scenario on this integrated level could be, for example, as shown here, we have a client and a server running on one processing module. They communicate with each other on this processing module, but we might want to do reconfiguration. And the client and server, which were previously running on one processing module, are now split up and running on 2 different processing modules and only communicating through a router. And as said before, because we have some more passive communication now, we have to think about these added latencies maybe, or this added overhead from the reconfiguration. But just as an example to show what dynamic reconfiguration could be on an integrated level. More information on that also in the source references shown here in the bottom right of this slide. What we're mostly concerned with in this demonstration and this presentation is the dynamic reconfiguration on a module level. So we're not on the integrated level anymore with different processing modules, but we're looking inside of one processing module. And in that, we can have, for example, here, 3 partitions running. And there might be one partition which has a fault at some point during runtime, and we would like to deactivate that and activate a spare partition, in this case, partition 3, which then takes over functionality from the faulty partition 2. And PikeOS supports 2 different variations for dynamic reconfiguration, as shown here. On the left, the reconfiguration with partition mode changes through a dedicated health monitoring partition and ARINC 653 Apex functions, as well as the other variation, which is shown on the right in this figure, the reconfiguration by triggering a schedule change through the Apex function set module schedule. So usually you have one configuration deployed for each module in a system, in an IMA system, but you could also have multiple ones and just switch between these schedules in the configuration. What we are showing here in this demonstration presentation is the left variation for dynamic reconfiguration, but practically PikeOS supports both. So if we look at another scenario now on the module level, as shown here, we might have 5 partitions running with different frequencies. And what we've done is run these 5 partitions in a simulated environment, specifically in Simulink, to simulate a dynamic reconfiguration scenario. And we inject faults in 3 of the 5 partitions, and this in turn sets a reconfiguration scenario. What we noticed is that the executions of all partitions are shifted due to added latency from this reconfiguration. So we have to think about the added overhead when we do something like reconfiguration. We can't just say, okay, here's our system. We would like to have a safety net. We're doing dynamic reconfiguration to make the system more dependable. No, we also have to think about the implications of that. So there's going to be some added overheads because we're using additional functionalities to do the reconfiguration and set up spare partitions, for example. But this is just one example. I added another reference here at the bottom right of this slide, which you could, of course, also check out. And dynamic reconfiguration is also aligned with a lot of standards and guidances found in aerospace and especially aviation and avionics, like, for example, DO 297, which specifically talks about configuration data, which may be used for adaptation of the software, or ARP 4754 and 4761, which talk about redundancy, monitoring, and partitioning, as well as component failure and reconfiguration scenarios coming from that. And coming back to the overarching topic, so Juan talked before about modeling the overall software architecture first on a high level, maybe with a single source of truth methodology, and then exporting the metadata and generated code from that, which we can do from Simulink as well. And we're also doing this here, which we're going to show in the demonstration later. This metadata and the artifacts can be imported in Codio, which is SYSGO's integrated development environment, to create a PikeOS image, which can then be loaded on a target platform. But before we show the demonstration, Matthias is going to show us a little more PikeOS.
Thank you, Bojan. I will start with an introduction to PikeOS and how SYSGO's tools simplify the integration of the previously presented architecture on an embedded system. PikeOS is an embedded operating system designed for safety and security applications. So it combines the determinism of a real-time operating system with the flexibility of a hypervisor. This means in reality you can host critical applications alongside rich guest operating systems thanks to its separation kernel architecture. PikeOS provides the separation environment through partitions, which can be thought of containers which processor time and resources can be allocated to. Within these partitions, multiple application environments are supported. They include PikeOS native to run without any overhead, or APIs like POSIX or ARINC 653 for easy porting of existing applications, and by using modern hardware virtualization techniques, also other operating systems like Windows or Linux. These environments can also be combined in a single system, providing a mixed criticality architecture where applications of different severity or criticality can coexist on the same hardware platform. If one partition fails, it will not influence the others. PikeOS is available for different architectures like x86, ARM, PowerPC, or RISC-V. It has built-in multi-core support. In terms of safety and security, it is generally safe to say that PikeOS can be certified to the highest level of all major industry-specific safety standards. This includes, for example, DO 178C for avionics, ISO 26262 for automotive, or for security certification, the common criteria. The way that PikeOS is designed is modular. So if you take a look at the diagram here, everything that you see in green is prepared to be certified in a specific architecture. So you can think of this as the core delivery of PikeOS. This includes the architecture support package, the main microkernel, and the PikeOS system software with the native PikeOS API. Beside this, then we have in the blue section certified APIs depending on the application environment being used, which also includes the Apex API for the ARINC 653 standard. In this context, also some certifiable libraries are available, like the certifiable math library or an UDP IP stack. This reduces the effort of developing safety-critical applications by providing ready-to-use functions. The platform support package in red can be thought of as a very minimal board support package. We do have some of these available, but typically this is done in the context of the customer project, since there are usually some requirements that are quite project specific. So these modular components that I have spoken about are supported through the certification kits that we offer, which include the necessary safety manuals, erratas, artifacts, etc., offered alongside support and maintenance programs to ensure the certification process goes smoothly. Our Eclipse-based integration development environment, Codeo, supports system architects and developers with graphical configuration tools. It provides all the components software engineers need to develop embedded applications from code editor over system configurator to debugger and monitor. In the center, you see the graphical user interface to configure the target system, where you can easily create and configure application partitions. To these partitions, you can then assign the desired application executable and configure its system resources and time scheduling information. Codeo also includes comprehensive little helpers to finish embedded projects efficiently. It supports remote debugging down to the hardware instruction level. And with the addition of PikeOS development tools into the system image, you get access to detailed runtime information through target monitoring, where running process, threads, and system resources can be analyzed. To get an idea of the environment, we also have mini tutorials showing the essential functionalities of Codeo, so there's a link to have a look at it. Now here you can see the steps involved in the integration from model to target. So the system engineering part was presented by Bojan and Juan earlier, and now I'm focusing on the software integration part. Coming from a MATLAB Simulink model, which uses the ARINC 653 block set for process definition and partition communication, an XML-based system configuration can be generated. This configuration provides the information transfer from MathWorks model-based engineering into SYSGO tooling for embedded end systems. It includes the partition definitions and associated applications, port-based communication channels, and time scheduling information. The configuration can then be imported into Codeo to configure a target system for the defined architecture. Because we use the ARINC 653 Simulink block set, the standardized OS API is used. Simulink models can generate code for this API, which in turn is understood by the PikeOS Apex personality. This means that we can compile the output from Simulink embedded coder into a valid PikeOS Apex application executable and put it onto a PikeOS partition. To create these executable, we can configure Simulink to use the PikeOS toolchain, for which we provide the necessary toolchain definition files. For future enhancements, we are also working on a Simulink compatibility layer to provide support for PikeOS native API as well. This will allow to use the presented workflow also in non-avionics domain, as it removes the dependency on the ARINC 653 API, which is mainly used in aerospace context. As I mentioned before, the XML-based system definition can be imported into Codeo. Here on the right side, we see the generated partitions and ports. Port-based communication channels are automatically created and linked based on the imported configurations. These are the light gray ports here, and others can be added manually if needed. But the main idea of the process is to have them defined on a higher level and being imported automatically. In this way, there will only be a single source of truth for the target system. In addition to the resource partition setup, the time schedule is also generated from the periods and durations of the ARINC 653 processes. Here on the bottom, you see the graphical representation in Codeo, where the color-coded application partitions are assigned to time slots during a major time frame of periodic execution. With these generation features, the main system architecture can be defined on a higher level, as we saw earlier, and then brought onto the target device with the click of a button. After reviewing the integration setup, Codeo collects the selected applications and put them together into a runnable PikeOS target image to load onto the hardware. And there, of course, the runtime analysis tools provided by Codio can also be used to do evaluation of the final target integrated system. Now that we saw all the steps in the workflow from highest to lowest level, I hand back to Bojan to show you a demonstration of it in our use case.
Thank you. So I think Matthias said it quite nicely already. We're following a single source of truth development methodology for our system. And this pretty much means that we're going from a single source, high-level system architecture, which we're modeling in System Composer, through Simulink for code generation and binary configuration, and Codio, the integrated development environment, all the way to the target platform. And the PikeOS image that we get in the end that we're loading on the target platform comes from a single source. So this gives us a lot of advantages, like, for example, much better traceability and much better overview of our overall system. But with that, we can go to the video. So what we're showing here is, first of all, the modeling of our system in System Composer. What we've seen in the beginning is a profile that we're using for System Composer. It's an Integrated Modular Avionics profile shown here with all the attributes that are needed for the XML configuration file, which we need in the end. And this profile gives the modeler the obligation to model their system according to some structure, like a blueprint. This helps avoid some errors and follow perhaps the hierarchy that is needed for the system. What we're doing here, we can see we're creating two partitions. They're connected with an interface, in this case, a sampling port for both interfaces. So we have a flight controls partition and a redundant counterpart, flight controls 2. Bear in mind that this is a minimal working example because we didn't want the video to be too long. This could scale up as well and be arbitrarily large, but we have only two partitions in this example. We use our custom script to create the XML configuration file, which I talked about before. And we can see we have all the metadata and the information that we need, like the partitions, their duration, periodicity, and their ports. And from this, with some custom MATLAB scripts, we can create our Simulink model, which also uses a profile or a library. This profile is called ARINC 653 block set, and it also gives the modeler the obligation to model their system according to some predefined structure, which helps in modeling, of course. Here I'm adding a custom logic to one of the partitions, a very simple logic. It's a counter, just for demonstration purposes. Like I said, it's a minimal working example. And for these two partitions now, which are ARINC 653 partitions, I can generate code in Simulink. So why are we doing that? Perhaps instead of going straight to the binaries, which I'm getting into in a couple of seconds, we might want to generate the code and then work first with the code and customize it. In this case, this is C code. We can see that the custom logic that I modeled before here is also inside of the code. But in this case, we're not directly working with the code, but rather creating the images or the binary files that are loaded in the Codio development environment later. So we're running the toolchain. We can see that the model is built with the two partitions, and we can see the two binaries here on the left, two ELF files. We switch to Codio, which we can see here, create our model or our system setup for these two partitions, and we select the board on which we would like to deploy later, which is a PowerPC board in this case, a VPX architecture. And once the Codio environment is set up, we can create our two partitions, flight controls and flight controls 2. We can change the process names, the IDs, and Codio, the integrated development environment shown here, can be used to do some more low-level configuration, which we couldn't really do before. We can also adapt the scheduling, the channels, the shared memory of the system that we're developing. And Once we set up the two partitions here in the project structure, we then link the binary files which were generated before from the Simulink modeling environment here with their partitions. So here's the step where we use the generated binary files where we link them in Codio. Then we adapt the scheduling according to the configuration which we generated from our system composer model. This can, under some circumstances, also be done more automatically, where we just load the generated XML file directly into Codio and it generates our project structure from that. It also gives us some more automation. Once we're done with everything, we can build our final image file in Codio, shown here. So we built the project and we have a final image file just shown here, which we can then deploy on our target platform. So here's another setup, a laptop which is connected to our target platform, the PowerPC board. And with TFTP, we load the PikeOS image with the two applications on the board. And as we can see here, once we boot it, we can see a sample output from the two partitions, flight controls and flight controls 2, to show that they're working and instantiated on our target platform. And maybe to emphasize it again, why are we showing you all of this? So I created this in around 15 minutes. This video obviously is sped up, but I could create my system composer model in roughly 5 minutes, then create the custom logic in Simulink after importing the XML file within a couple of minutes, and then do the final changes in Codio and create my final PikeOS image. And all that within 15 minutes. Of course, this example here is quite minimal, but this scales up quite nicely. And we also have another example in one of our papers where you can also see technicalities. But with this whole setup, we have a single source of truth method which we follow for easy deployment from a high-level system overview all the way to a target platform. And with that, back to you, Franz.
Thank you, Bojan. And thank you to all presenters. So let me summarize. So what you can do is capture software architectures early in the system composer as single source of truth and export them into Codeos, or the PikeOS IDE development environment. And you can generate application code from Simulink and integrate it into the PikeOS partitions. And you can use the partitioning standards such as ARINC 653. Via that, you can profit from reduced manual integration efforts and improved traceability from high-level components to code. You can profit from facilitating the compliance within your certification process. And finally, you can profit from a proven cooperation between SYSGO, MathWorks, and ready-to-go examples provided by DLR. This is just a summary of a couple of white papers that we have already published. Please be invited to download them. So you have white papers around systematic approach to model-driven development, or on EMA with MATLAB Simulink on the ARINC 653 block set, or the video that was shown here is also published on YouTube. So then we are approaching the end of the webinar. I would like to highlight the different partners that have provided their content to this webinar with the links here. So with that, we hope you liked the content. I would like to thank all presenters and the organization team, and hope to see you again in this channel for future topics around mission-critical embedded systems. Thank you so much for joining.